This is Mrs. O'Neill for AP Chemistry, Chapter 15, Section 3, Understanding and Working with Equilibrium Constants. You should have watched the intro lesson on the equilibrium constant. So here are my notes. He talked about this particular reaction, which was a chemical weapon used in World War I, and he talked about, let's talk about that K value. What does that really mean? Well, here's the overall reaction, and in this case, we have a large equilibrium constant value. All that means is that we have a heck of a lot more products than we do reactants, and that's what you want in this particular situation. So what is K? K is just a measurement of how or when we would reach that equilibrium. If we would have more reactants when that equilibrium is established, or do we have more products when that equilibrium is established? So that K value just tells us, do we have more reactants or products in our overall equilibrium equation once equilibrium has been established? He used a nice PhET model to give you some more insight on the information and how this ratio, this K equals products over reactants, works. Then he talked about a chemical reaction, and here that equilibrium constant equation. And again, we already know that it's products over reactants. We want to remember that if you have multiple products, they're going to be multiplied with each other, as well as reactants, they're multiplied. But you also want to remember that the coefficient from the balanced chemical equation is actually an exponent. So we want to remember to include those also in our expression. So he talked about a large K, meaning that there's more products, means that there's more on top. That should make sense. Again, this is a ratio. So if you have a bigger number on top, that means you're going to have a large K. That means you have more products. Now, he also talked about heating up this reaction. And he said if we heat up this reaction, K actually becomes smaller and it's going to shift to the left. You're going to understand that in more detail when we get to Le Chatelier's principle in section 7. So right now, again, all you need to understand is that a small K means that you have a bigger number on the bottom. And if you have a bigger number on the bottom, that means you're going to have a small value of K and you have more reactants when that equation reaches equilibrium. And he also talked about heating up this reaction means that K would become larger and the reaction would shift to the right. Again, we'll talk a little bit more detail about that later. But you do want to remember that K is very temperature dependent. That's the one thing, that temperature, even though it's a constant, will change because of the temperature difference. So again, this is just a nice visual to get you to understand if K is a large number, greater than 1, you're going to have more products in our overall equilibrium reaction. If K is a small number, less than 1, we're going to have more reactants in our overall reaction. So let's look at this way. Let's put in real numbers so you get that understanding, that true understanding. So here's K, and if we have products over reactants, and we're going to use easy numbers like 2 over 1, 2 divided by 1 is 2, which is a large number, and that means we're going to have more products because we have more or a bigger number on top of our ratio. But if we switch those numbers around, now we have a 1 over 2 for our products and reactants. Now our value is 0.5. And that's a small number, or smaller than 1, and that means we would have more reactants. So if you're still unsure, or you get like messed up or tripped up, plug in numbers, products over reactants, plug in a number, you make them simple like this, or use 5 and 10, whatever the case may be, so that you're understanding that ratio and what it does. So on to your notes packet. Here's our objectives: to interpret the magnitude of an equilibrium constant and how its value depends on the way the corresponding chemical equation is expressed. And again, we're going to go back to the balanced chemical equation and how those coefficients really affect our exponents in our equation. So at this point, pause the video, fill in the notes, and then play to hear my words. So the magnitude, this is something we've just discussed, right? It's a relative measure of how far the reaction will go, or will there be more reactants as the reaction is equilibrium, or will there be more products? So again, this should make sense to you. And again, here's our reaction, or our reaction and our equation. And again, we have products over reactants all the time. So of course, if the equilibrium constant is 1, that means that they're equal to each other, the amount of reactants and products. That actually doesn't happen very often. So most of the time, you're either going to get a number greater than 1 or a number less than 1. So pause the video, see if you can put I, and I in order from increasing K value. So in other words, your smallest K value to your largest K value. And then do you understand the why? Can you give a reason? Hopefully you got that information, and again, you're just kind of counting the dots, and this is something that the AP people like to do, give you some kind of visual, and then how would you explain it? Well, there's more products, meaning that you have a larger K, your value on top of your ratio would be larger, all of those good things. So remember these two graphs. Do either of these two graphs indicate actually if the KEQ is greater than 1 or less than 1? So again, pause the video and think about it. Would these, if they would give you a graph, could you say, looking at this information, is the equilibrium constant greater than or less than 1? Hopefully that made sense. You have more reactants. If you have more reactants, your K value here is going to be less than 1, meaning that the reverse reaction is more favored. So let's look at how to manipulate an equation and relate it to K. So there's 3 ways you can manipulate an equation. A reaction can go forward, and we can take a reverse reaction. So if I give you one reaction and then I reverse it, what are you going to do to K? Well, you're going to take 1 over K, or the inverse. If you're multiplying a reaction, so let's say we double a reaction, meaning we double those coefficients, really what we're doing is we're raising that power, we're squaring it. Okay, so that's a little tricky. Okay, you're not just doubling, even though you're doubling the reaction as far as the coefficients go, you're really not doubling the K value. You're actually going to square the K value. And just like delta H, when we talked about Hess's law and adding up all those Ks, in this case, we're not really adding the Ks together. We're going to multiply them together. So let's look at some examples here. So if you want to pause again, see if you can come up with a value and the Y. So in this case, we reverse the reaction, so it's going to be 1 over that K value of 0.02. So it should make sense to you. If we have a forward reaction in this case, and it favors the products, and if all we did was reverse it, now the reactants basically became the products. Again, that should make sense to you because of the ratio. How about if we multiply a reaction? What did we just say? We're going to square that reaction. So we get a value of 2,450. Seems a little weird, but that's really what happens to that K value because of what we're doing to the numbers in that equation. So again, if you're really not truly understanding, please, please, please come up with some numbers, come up with a molarity for each of these substances, plug it into K, and then take them and do the doubling the reaction. Will square those coefficients, make those exponents bigger, and see what it does to your K value. Give it some thought. Hopefully that makes sense because you went from a 2 to a 6, so you cubed the entire coefficients of that balanced equation, so you're going to cube your K. And again, I'm showing you here as Kp instead of Ka because all of these are gases, so remember that we can also talk about gas pressures as a constant. So here again is another example of multiplying reactions. So here we have reaction 1, reaction 2. Here's our overall reaction. So we would actually take those 2 K values of the individual reactions and multiply them. Again, but the setup's the same. Products over reactants, and our coefficients are our exponents. And so we'd end up with a total reaction like that, or a total expression, constant, equilibrium constant expression of that sort. Okay, see you in class.